Welcome. Today's notes worksheet is entitled Normal Distributions Day 2. This most certainly is a continuation of the previous notes worksheet, primarily dealing with the introduction of normal distributions. But what we want to do today is move a little bit beyond the 68, 95, 99.7 rule and see if we can develop some ideas for values that are a little bit different than 1, 2, or 3 standard deviations above or below the mean. So let's talk about what a standard normal distribution is. In fact, that's how we ended that last lesson, talking about the fact that we're going to take our density curve that is normally distributed and standardize it. So here's what I have. It is a normal distribution, capital N please on the normal. So normal distribution with the mean being a uniform number, and that mean is going to be 0. And standard deviation of exactly 1 unit. And obviously there's a little formula that's going to go into this so we can standardize our values once we get our data distribution, or at least the 2 specified numbers from our data distribution, being the mean and the standard deviation. So here's what I have. The formula, if a variable, and we'll just call the variable x for the time being, and primarily this is going to represent an observation in the data distribution. So has any normal distribution and just if you remember the notation for the normal distribution, little capital N right there, there's our mu and there's our sigma. Then very simply, the standardized variable, and we saw this of course once before. We're going to use our z-score, so here's our z value right here, and it's very simply the observation minus the mean over the standard deviation. And that would produce the standard normal distribution. So again, we're just going to develop a couple ideas based on this idea right here and this formula, and see what we can do with a couple examples. All right, so you see our nice standardized normal density curve right here. Here's your mean, of course, with 0. And each value is 1 standard deviation away, so we use this as 1, another 1, and another 1. So 1, 2, 3 up, 1, 2, 3 back. And obviously moving to the left, below the mean is going to be negative, and above the mean is going to be positive. All right, good. Good little visual there to get us started. And then let's go into the next piece. So it says on your paper, because all normal distributions are the same when we standardize, okay, so they're all going to have this shape and these values when we standardize them, we can find areas under any normal curve from a single table, conveniently referred to as the standard normal table. A table entry for each value z is the area under the curve to the left of z. So guys, if you don't mind, take a moment and just underline that piece for me. And we'll just go ahead and use this. If and when you decide to take a statistics class, you'll see these tables in quite more of a complete form. But I went ahead and pasted this in just to use for this example right here. But primarily, we will use the calculator to find our values as opposed to a table. But I just wanted to introduce that concept as this is a big notion in stat. Okay, example 1. It says interpret the table value or the table entry that is circled, then use a calculator to confirm the table entry. Okay, so obviously there is not one circled right there, so I'm going to have you circle it yourself. And this is the one I want you to focus on, so can you just circle that one? And it's pretty arbitrary. I just kind of picked one off the top there. And so here's what we basically have. We have a z-score that goes with it, and in this particular table, it sort of has the 10th values here and then the 100th values here. So here, if I sort of cross-reference it, it looks like the z-score is going to be 0.42. Is everyone okay with that? So this has a z-score right here of 0.42. And so this value as it says, for a particular z-score is the area under the curve to the left of z. All right, well, let's first do this, I guess, in maybe a visual manner, and then we'll go ahead and do the interpretation. Then we'll use the calculator, and hopefully it'll all really click nicely. So first and foremost, let's go ahead and just draw the standard normal distribution and its density curve right there. And here, of course, would be 0. And right here would be 1 standard deviation away. So on the standard normal distribution, that value would be a 1. And so what we're looking for here is the z-score that is 0.42. So what that means is 0.42 units above the mean in the standard deviation. So that's what I'm looking at right here, everyone, 0.42. And notice what it says. The table entry for each value is the area under the curve to the left of z. So there is our z value, everybody, of 0.42. Just one more time, 0.42. And so what we have here would be the area under the curve to the left of it. Now, of course, please remember that the area under the entire curve would be 1, or 100%. So the area to the left of 0.42 would be 0.6628, it looks like. It's tough for me to see this, actually. 0.6628, or 66.28% of the data values to the left of that. Does that make sense? Think about that for just one more minute, and then we'll kind of write it in place. And then again, we'll use the calculator to do it as well. So just one more time, very fast. Here's the z value of 0.42. What that means is obviously between 0 and 1 standard deviation, right there, 0.42. And that value represents the proportion of observations to the left of that z value. Okay, well, let's put that. So here's what I have. Kind of putting it as a full sentence here, and if you want to paraphrase this, you're more than welcome to. But essentially, it's the proportion of observations from the standard normal distribution. That's the key. So I might have to shorthand a little bit here, but you'll get the idea. So the proportion of observations from the standard normal distribution less than 0.42 is equal to, or is, and I'm sorry, I'm going to have to come down here, 0.6628, or very simply, 66.28%. So remember, we kind of talked about it on the previous notes worksheet where we were 1 standard deviation away, or 2, or 3, but if we were not exactly on those values, we couldn't find out the proportion on the curve. We couldn't use the 68, 95, 99.7 rule. So by using this and standardizing it, and at this point using the table, we can sort of figure out proportions less than, or greater than, or between, and kind of work our way through. Okay, so let me just read that one more time, and then we'll verify on the calculator as well. So the proportion of observations from the standard normal distribution less than a z value of 0.42 is 0.6628. Perfect. Now, guys, bring up the calculator if you would. Show you just one thing. So we're looking for less than 0.42. What percentage of the observations are less than that in the standard normal distribution? So grab that calculator, everybody, and you're going to hit the second button for me. And in this one right here, DISTR for distribution. And we're going to go right here, the number 2, normal CDF, if you would. So go down to number 2 and hit enter. And what you have to essentially do is create a lower bound and an upper bound. Now, if you remember, for this particular problem, we just wanted to the left of 0.42. So there's no real lower bound here. But we still have to give the calculator some value. And it's up to you. I'm going to use negative 100. So basically going all the way to the left, we can use really any large negative, and this would suffice. I'm going to use negative 100, and it should work for our purposes here. So I want to go from negative 100, which would be a z-score, all the way out here, really covering just about everything going to the left. and then all the way up to 0.42 as our uppermost boundary. And as you can see, when we hit that, we end up getting, notice in the table, 0.662, and they round it up there, and so 0.6628. Okay, so I hope that makes sense, using sort of the table to help us, and then this is how we'll use the calculator as well. We'll make the transition momentarily. All right, cool. Let's do example 2. Same deal. Use the table to determine the proportion of observations from the standard normal distribution greater than 0.64. So just an arbitrary z-value, just something that I found in this clip of the table right here. Obviously, there are plenty of other z-values not included in my little table right here. But let's see if we can find what we're looking for. Let's do it visually if you don't mind. So everybody, a little standard normal distribution curve, something like that. Here's your 0 right here. And here would be your 1. And I see we're looking for 0.64, which would be right here. And we're actually looking for all the values greater than. So as I shade, that would be this piece. So let's find a z-value, of course, of 0.64. So here's the 0.6. And just cross-reference it with the columns there. And it looks like it's going to be this piece right here. I guess I'll go ahead and box that up. And it's tough for me to see, but that looks like 0.7389. So 0.7389. Now here's where we have to be careful. That 0.7389 represents the proportion of observations to the left of our z-value. So 0.7389 would actually be everything here. So about 73.89% of the values are to the left of the z of 0.64. So what do you think I'm going to do to find the values to the right of 0.64? Well, I hope you would certainly agree that it's basically going to be the 100% or the 1 minus the entry in the table. So 1 minus 0.7389, and that should hopefully give it to us here. And I get about 0.2611. And so what that's basically saying is, in the standard normal distribution, 26.1% of the observations are going to be above a z-value of 0.64. Okay. Hope that makes pretty good sense. Let's go ahead and confirm it on the calculator. So same deal, guys. If you would, go second to that distribution and just go down to the number 2. And in this case, again, you just need a lower bound and an upper bound here for this. And in this case, it looks like the lower bound is 0.64. And then the upper bound is, it really just goes to infinity here. You need to put in some number. You could do 100 or 1,000, I've seen as well. It really doesn't matter a whole lot. It's not going to make a dramatic difference. But when you put that in, and what did we say about 0.2611? And there it is. So 26.11% of the values are above a z-score of 0.64. Cool. All right, let's do example 3. Look at it visually and then kind of go from there. It says use a calculator to determine the proportion of observations from the standard normal distribution between a z-score of 0.36 and a z-score of 0.75. So theoretically, we could use the table up here, as I think I have these z-scores up there. I don't think that we're going to do that. I think we're just going to go ahead and use the calculator at this stage, and really, for the most part, most of the rest of the way through. So guys, let's be visual about it if we could. Here's your 0 right there. And so there's your 1. And 0.36 would be basically right here. 0.75 would be right in here. And we're looking for all of the observations, or really the proportion of observations that are in between the two. Sorry, that's poorly formed right up there, but that's all right. I think it should still work. So in between 0.36 and 0.75, and again, the calculator really works out nicely with this type of stuff. So go to that distribution if you would. Number 2, in between 0.36, put the comma in place to 0.75, and that's what we end up getting, about 0.1328. So in this case, I'll go ahead and put that up here, 0.1328, or again, 13.28% of the observations in between those two scores. All right, very nice. Hopefully it's starting to click here. Let's go ahead and try a more complete example. So I exercise on an elliptical and using a cardio program, and I go for 30 minutes. And so my distance covered in the 30 minutes time frame would follow a normal distribution. And I cover with a mean of 2.41 miles. And the standard deviation for my distance covered is 0.03 miles. So I've got my mean, standard deviation, normal distribution. I think we are ready to go. Now these values, as we're going to see, do not really necessarily fall on the 1, 2, or 3 standard deviation. So the 68, 95, and 99.7 rule might not be sufficient to answer these questions. But let's see what we can do. So how about this, just if we get a moment, let's go ahead and just sort of draw what we have going there. And I'm going to just do the non-standardized version initially, just based on what we have from the previous lesson. So I think 2.41 was my mean, and one standard deviation would be 0.03, so that would be 2.44, 2.47, 2.50, et cetera, et cetera. Let me go on back if you don't mind. You do the same, please. It's kind of good to draw this out a little bit. And then 2.35 and 2.32 on the lower end there. Looks good. Now again, what we're going to basically do is standardize that. So if you get a chance, just right below, let's just go ahead and draw a very similar bell-shaped curve there, so the normal density curve. And so standardizing it would mean that the 2.41 would represent a z-value of 0. 2.44 would represent a z value of 1, and 2, and 3, of course. Anything below the mean just goes negative. And we've got those pieces. So this is the non-standardized version. This is the standardized version of those values right up here. Okay, well, let's see what we want to do with this. I do see, just kind of looking at this, we want percent of exercises greater than 2.44 miles. Now, it just so happens in this particular case, you see 2.44 is right on one standard deviation. So could I probably, if I really wanted to, start thinking about the 68, 95, 99.7 rule in order to find out this piece right here. And again, I'm not going to actually shade it in, but that's what I would be looking for. Greater than 2.44 miles. Sure. But what I want to do is use the standardized version for today. So first and foremost, what we want to do is standardize the 2.44. And what that means is coming up with a z-value for it. So we take our observation. Now we use that formula from the front side. We subtract the mean and divide by the standard deviation. And again, it shouldn't be a great shock here. No calculator necessary. If we did this, we end up getting a z-score of 1. So what that now means for us, of course, nice and easy, guys. Just it's the normal CDF on the calculator, where we want greater than 1 standard deviation. So again, that would be now standardized everywhere to the right. So something like that. And so what do you say we just go from 1 to 100 and see what we end up getting? So what percent of my exercise is greater than 2.44 miles? Well, let's find out. So go to that distribution if you would, number 2, and from 1 to 100 should suffice. And there we go. So about 0.1587, give or take. That's exactly what I'm going to put up here. And you can definitely write that as your answer. I'm going to go ahead and box that up just to make sure that everyone sees that is our final answer. If you want to write it as 15.87%, you're of course more than welcome to do that. Okay, either way, a proportion compared to 1 or a percentage of 100. All right, letter B. What percent of my exercises are less than 2.4 miles? So do you remember this one? Thinking about this yesterday, if I asked you less than 2.4 miles, would our 68, 95, 99.7 rule work for this? No, of course not. but I still want to go ahead and see if we can solve this mathematically, and that occurs by standardizing this. Where does this fit in terms of a z-score? And so now let's take a look at this. It looks like we want to get a z-score from here, 2.40 minus 2.41, and let's divide that by 0.03. And again, should probably be able to do this without a calculator. I'm going to bring it up just in case. But to standardize that, we go 2.40 minus 2.41, divide that by the standard deviation, of course, and it looks like we get negative 1/3. All right, very nice. So z value is negative 1/3, which again, if I went to kind of look at this, that would be right in here, of course, which matches up right there. So there is my z-score, and I'm looking for anything less than 2.4, so that would be from here all the way to the left. I don't want to actually sketch it in, but hopefully you can kind of see that. And that looks good. Well, not too bad. Everything's ready. So less than this z-score right here. What do you say we just go from negative 100 to the negative 1/3? See what it's equal to. All right, bring the calc up. And so lower bound, let's go negative 100. And upper bound, negative 1/3. And I think we're ready. So I get about 36.94% of the observations or of my exercises would be below 2.4. Super. All right, so let me just make sure I get that number in right. 3694 on that. Looking good. Okay, letter C. What percent of my exercises are greater than 2.36? So just kind of looking up here, greater than 2.36, about right here, give or take, all the way to the right. So chances are our z-score is going to be in between -1 and -2, right? Somewhere in there, and it should work. So let's go ahead and standardize that 2.36. By now, hopefully it is clicking. Get that right there. And if you do this, just to save ourselves a little time and energy, this looks like a -5/3 if I see it correct. So again, we're looking for a standard deviation of -5/3. I'm sorry, a z-score of -5/3, and we're looking for all the observations to the right of that. So rather than kind of using the table and have to make interpretations, let's just go ahead and do our normal CDF. And lower bound is -5/3. Upper bound, let's just do as 100, and should work. Okay, it's coming up for the third time on this problem. Here we go. So -5/3 on this end. Throw the comma in, everybody, if you would, and 100. And so in this case, it looks like over 95% of the values or of these exercise times would be above, what was it, 2.36? Okay, so 0.9522. Looks great. Last one. So between 2.37 and 2.43. Here's 2.37. Here's 2.43. What percent of the exercises are between those two values? So it looks like we're going to have to get a couple z-scores out of this. Okay, maybe you can do this now a little faster than what I have going on up here, as hopefully you are developing a nice rhythm with this. So I'll get my 2 z-scores and then we'll put this in place. So same thing with the 2.43. Good. So if you use the calculator for this one, looks like you get a z-value of -4/3. And if you use the z-value for this one, looks like you end up getting 2/3. Looks great. And so that would be pretty much from here to here. Again, should match up with what I had up there. I kind of like the non-standardized version, and then right below it, the standardized version. Looks really nice. So let's go ahead and do it one last time on this one. Normal CDF. And let's go -4/3 to 2/3. Bring up the calc. And now you can do it pretty fast, can't you? So what did we say? Negative 4/3, comma, 2/3, and there we have. So what percentage of the of the exercises, in between 2.37 and 2.43 miles, it looks like a little over 65%. So 0.6563 is what I have. And you start to see sort of how the calculator works some of these values out. Looks great with that standardization. Super. Let's see what we've got coming up next. So example 5, kind of taking a little different perspective on it. Let's see what we can do with this piece. And then quick example 6, and we'll round this out. So example 5, the assessment grades in my pre-calc classes are approximately following a normal distribution. And mean is going to be 83.5, standard deviation of 5.5. And it says, what is the first quartile? Oh, interesting. First quartile of the distribution of grades. So do you remember first quartile? We've seen this phrase before when we did kind of a box plot. And sort of the first quartile, what does it really mean? It's sort of the 25th percentile. Do you remember that idea? So we talked about percentiles when we describe a location in a distribution. So I'm just kind of thinking out loud with this, but as soon as I hear first quartile, what that does mean is the 25th percentile. Well, let's go one step further. What does the 25th percentile mean in a data distribution? And let's actually write this down, again, just kind of thinking out loud, but it is the value of x, that's what we're looking for here, the value of x, 25th percentile means 25% of the distribution is to the left. So it's the value of x with 25% of the distribution to the left of it. Interesting. All right, so, and you know, we could do this a couple different ways, but I like to be very visual about it. So here's our standard density curve right there, and I'm going to just have to ballpark this to be honest, but essentially there is some z-score in here that we're going to have to find. I think that's our first step because obviously the title of this is all about standardized normal distribution. But basically 25% of the values are going to be to the left of some z-score. So at this stage, guys, I'm seeing this, and you don't have to write that in just yet, but there is some z-score where the area is 0.25, right? Because 25% of the distribution is to the left of some z-score right here. Interesting. Now we could probably use a table if we needed to, if we had access to it. There just happens to be a way on the calculator to find this z-score. So if you remember what we've been doing before, especially in the previous example, I'd give you the z-score, you would give me the area to the left of that number. Now I have the area, now I need the z-score to match it. And so there happens to be a nice little calculation right up here. Go back to that same menu if you would. And remember what we did here. We talked about that normal distribution. Here it is. We're going to do essentially the inverse of that. So go down to number 3, guys. And I'll put this on the board in just a second, but essentially we're going to do the inverse norm of 0.25. So this is saying 25% of the observations are to the left of some z-value. I need the z-value. And there it is. Cool. Now we're going to round to a couple decimal places on the z-score here and then go from there. But let's go ahead and write down what we did, and then we'll go for it. So calculator-wise, everyone, we did inverse norm, 0.25, and that gave me, of course, a z-score of about negative 0.67. If you want to go further, you're more than welcome to. But essentially now, that's what I have going on here. And I think we probably all intuitively knew that the z-score would be negative. Obviously, the 25th percentile, we're talking about below the mean in a standard normal distribution. So I think that was fairly obvious. Okay, that looks great. And so just one last step. Notice what I was looking for originally, the value of x. I have the z-score to match the 25th percentile. Now what I'm looking for is the specific observation in the data distribution to match that z-score. Now, you don't have to do all of this on your paper, but this is the formula we've been working on, right? The z-score is the observation minus mu over sigma. Well, what's the only thing that's missing here, guys? The observation. So in this case, let's put in the z-score. What was the mean? 83.5. Standard deviation was 5.5. Now can we solve for the observation that's missing? Certainly. So what do we say we do this on the calculator in just one big step, but essentially what I'm going to do is probably multiply by 5.5, bring that up here, and then what do you say we add 83.5 to bring that over? So multiply this, add that, and that should give us our x. So now really just a straight up calculation. I'm just going to slide this over just so I have my numbers handy. So we take the z-score that the calculator gave us, about negative 0.67. And again, if you want to use this whole number, you're more than welcome to, of course. Probably be a good idea, but I truncated it to 2 decimals. Got that. And then add 83.5. And there we go. So what was the first quartile? About 79.82, somewhere in there, give or take. However you want to round, it's up to you. Just the way I had it go, and it gave me all the way to the 3 significance. So whatever, makes no difference. Let's go ahead and put it in, about 79.82. Awesome. Okay, so good one. Kind of reversing course there. Last one on the notes worksheet, example 6. It says, create a histogram using the data set of my biking time. So we have seen this before. Would you consider the data to be normally distributed? And then determine the mean and standard deviation and check whether the data set follows the 68, 95, 99.7 rule. Interesting. Well, let's go ahead and do this. And you do not have to create the histogram. I actually already did this. So don't waste your time putting it in. You can just kind of watch up here as I go through it, because as you'll notice, when I hit Stat and Edit, I took a little time and already entered them in. And as a matter of fact, if I hit Zoom in number 9, there's my histogram. And you can see, is it perfectly symmetric? No, but I'll bet you if we looked at it in a little detail, it is pretty symmetric. So, would you consider it to be normally distributed? Maybe just based on the symmetry there. It certainly looks pretty good, all things considered. We're going to do a little mean and standard deviation on this. And so as a matter of fact, we've done this before, so good little test. Do you remember where I go for those one variable stat? So I hit Stat, move it over to Calc, and there they are right there, number 1. So let's hit that one variable stat on this. And as a data distribution, notice we have a mean, which is 34.749. And we have the standard deviation, which is 2.059, again, of this data set right here. So we're going to use that piece and then just kind of talk about how it fits in with the 68, 95, 99.7 rule. And it would be a good culminating piece to the 2-day lesson here. All right, so let me go ahead and write a few things down. I think we're ready to roll with this. So my X bar from the calculator was 34.749. My standard deviation from this particular data distribution set was 2.059. And so we've got that piece, and now I guess I'd ask us, does it kind of follow the 68, 95, and 99.7 rule? Well, here's what I have on my paper, and then I'll ask you to kind of do the same. What I'm going to ask us to do is kind of think about the 68 part of it is the mean plus and minus 1 standard deviation. Well, when I think about the 95 part of that rule, it's really between -2 and 2 standard deviations of the mean. So just write that down, and I'll show you what I'm looking for in just a sec. And then the last part, of course, is the 3 standard deviations below and above. And so it kind of looks like this right here. So if I was to go ahead and find out from -1 to 1 standard deviations, -2 to 2, -3 to 3, these would be the intervals here. And I already did these calculations just to save us a little time and energy. But take a peek. Let's see if this does work. I'm curious myself. So if you're ready, if I go 1 standard deviation below this number and then above this number, it would be from 62.69 to, I have about 36.8, I have to read my writing there, I think 88. Okay, and then the 2 standard deviations would be from 30.63, oh, I see what I did, sorry, let me just quickly remedy this piece. Looks like I went a couple more decimal places out on this one, so I think this was 808. Sorry about that, 631. Good, let's get this in, and then to 38,867. And last but not least, the 3 would be from 28,572 to 40.926. Alrighty, now here is what I need you to do. You're going to pause the video for just a second, and I have 20 values, 20 different biking times that I recorded. And what I want you to do is figure out how many are within 1 standard deviation of the mean, how many are within 2, and how many are within 3. I gave you the intervals to look at. So pause the video, and then I'll show you what I got. Okay, you ready? So here's what I did. I looked at how many of these values were in between these 2 numbers right here, and as a matter of fact, 14 of the observations out of the 20 are between -1 and 1 standard deviation, which means that would be 70%. By the way, what's the rule, of course, for the 1 standard deviation? 68. Not too bad, right? Next one, how many were within 2 standard deviations of the mean? If you count them up, I believe it was 18 out of the 20, which of course would be 90%. Again, not bad. Pretty close to that 95 right here. And how many were within 3 standard deviations of the mean? As a matter of fact, all of them. So in terms of looking at the 68, 95, 99.7 rule, can we sort of think of this as being normally distributed? Yeah, not bad. It was pretty symmetric. And are my values following this rule up here for a standard normal distribution? Yeah. Cool. Alrighty. I like that. Good way to end that lesson. If you have questions on normal distributions at all as you go through those practice problems, don't hesitate to ask, of course. Thanks so much for listening.